Hello, this is Lab 4, where we examine oscillations. The purpose of this lab was to examine the motion of a mass oscillating in a spring mass system. From that data, a computational model was created and compared to the experimental model from Tracker. The resulting graphs of the computational and experimental models were very similar. To begin with, Newton's second law describes the net force as change in momentum over change in time. From this, the velocity and position update formulas can be derived. In addition, the total net force acting on the mass spring system is needed. The first interaction is the gravitational force, which is the negative of mass times the gravity constant in the y direction. Next, the spring force is the negative of the spring stiffness times the spring stretch or compression times the unit vector. In this experiment, the spring is stretched and it is found by subtracting the relaxed spring length from the current length. Furthermore, the period of oscillation is equal to 2 pi times the square root of mass divided by the stiffness. This will be needed for calculations of the spring. Finally, the total net force is the sum of the gravitational and spring force. Moving on, the other key principles for this lab are the energies of the system. First, the kinetic energy is 1/2 times mass times velocity squared. The gravitational energy is equal to the mass times the gravity constant times the length of y. Lastly, the spring potential energy is equal to 1/2 times the stiffness and the stretched length squared. Furthermore, the energy principle is the change in energy in the system equal to the work done by the surroundings to the system plus the change in thermal energy between the surroundings and system. In this case, there is no work done. Therefore, the change in energy is the change in kinetic energy plus the change in potential energy, which includes the spring and gravitational potential energies. In the video analyzed, the system is the mass, spring, and earth, while the surroundings are nothing. The given initial conditions were the mass of the ball, 0.402 kilograms, the ball's initial position at negative 0.64 meters, and the length of L, which is 0.7 meters. Since the ball was initially at rest, the initial velocity is 0 meters per second and the time starts at 0. To find the stiffness of the spring, the period of oscillation formula was set up to solve for K. First, T was found by calculating the difference of time between peaks, which was 1.492 seconds. The mass and T were then plugged into the formula and the spring stiffness resulted in 7.192 newtons per meter. Next, the relaxed length of the spring was found by setting the spring and gravitational forces equal to each other, and the equation is then set to solve for L0. The stretched length, the mass, the gravitational constant, and the spring stiffness are then plugged in. The relaxed length is calculated to be 0.147 meters. To start with, the initial energies were defined. The gravitational and spring forces were then calculated and added to find the total net force. Using the total net force found, the ball's position and velocity were updated. Then, the spring was updated using the ball's new position. Finally, the changes in kinetic, potential, and total energies were calculated by subtracting the initial energy from the calculated energy. Possible errors in this lab are from rounding and negligible factors. From the graph, the system's total energy was 0 and constant, while the other energies oscillated. The spring and gravitational potential energies had amplitudes of approximately plus and minus 4 raised to the power of negative 3 and were invertedly related to each other. The kinetic energy's amplitude and period of oscillation was a lot smaller in comparison. In addition, the resulting computational models were very similar to the experimental models from Tracker. A small difference in the x position graph is seen as the experimental model is slightly skewed. Based on the results of the lab, the energy principle is satisfied. The energy principle states that no energy is created or destroyed but can be changed from one form to another. Since the total energy stays constant throughout, the principle is satisfied. In addition, since there was nothing in the surroundings, no work was done on the system, so the total energy was 0. Once again, the period of oscillation is found from the x and y position graphs by finding the difference between peaks. The period of oscillation are relatively similar between the graphs, but differ slightly due to different motions. In the y position, the mass goes up and down like a vertical spring, while in the x position, the mass swings side to side. Thank you for listening.